This chainsaw is clearly running, yet touching the blade with a finger doesn't cause any harm. But when a stone is placed on it, the saw slices it open instantly. So what exactly is this magical saw? Why can it cut through hard stone but not cut a finger? Simply put, this thing is called a gemstone trimming saw. It's specially designed for dealing with hard stones like gemstones, and its core principle is grinding, not cutting. Gemstones like crystal are extremely hard, second only to diamond. Regular metal blades can't cut into them at all, so the edges of the saw blade are embedded or coated with diamond grit. Diamond is the hardest natural material known. When the high-speed blade contacts a gemstone, those diamond particles act like tiny chisels, scraping and grinding the gemstone's surface at high speed. By continuously and steadily pushing the raw gemstone toward the blade, these tiny grinding actions build up over time, eventually forming a cut that splits the stone apart. This process looks like cutting, but it's actually more like sanding glass with diamond sandpaper, just thousands of times more efficient. So why doesn't a finger get injured when it touches the blade? It's actually because our fingers are too soft. When the blade rotates at high speed and presses into a gemstone, each tiny diamond particle can steadily work on the stone's hard surface, removing a little material at a time. Those tiny particles need a hard surface to bite into to start grinding effectively, but when touching skin, the skin instantly dents and deforms, preventing the diamond particles from getting a stable point of contact to begin grinding, which is why the blade can't cut a finger. But note, this only applies to momentary contact. If you press your finger hard into the blade for too long, the result would definitely be bad. And when talking about saws that won't cut skin, there's another one everyone knows, the cast saw. Doctors use it when removing plaster casts. Just like the gemstone saw, this tool can easily cut through plaster, but it won't cut skin when touching it. It can't even pop a balloon. So what's its principle? Unlike the gemstone saw that cuts by grinding, a cast saw works by oscillating back and forth. The blade vibrates rapidly within a very small angle range, like countless tiny chisels breaking apart the microscopic grains of plaster, and that's actually why it doesn't cut skin. Skin elasticity allows it to move with the oscillation of the blade, and the amplitude of each vibration is too small. The force isn't enough to chisel through elastic skin. So the skin is pushed aside and immediately bounces back, instead of cracking apart like plaster. A battery can even be made into a knife. Wrap thin iron wire around two keys, then clamp the battery between the two keys. At this moment the whole setup looks completely ordinary, but when the thin wire touches the cup, you can see the cup being easily cut open. What exactly is the principle behind this? When electric current passes through any conductor with resistance, the current does work, consumes electrical energy, and produces heat. So it's easy to understand the principle of a battery knife. The metal keys and iron wire are conductors. Then the battery, keys, and iron wire form a closed circuit. Current flows through the circuit. As we mentioned earlier, current passing through a conductor produces heat, so the iron wire's temperature rises, creating a cutting effect. But have you ever wondered, in the same circuit, why doesn't the hand touching the keys get burned? The answer is that conductors with greater resistance generate more heat. According to Joule's law, Q equals I squared RT, where I is current, R is resistance, and T is time. The keys and thin iron wire are in series, so the current is the same, and the energizing time is the same. But the iron wire has greater resistance than the metal keys, so the wire generates more heat and reaches a higher temperature. Then when the wire touches the cup or foam, heat is transferred. The cup absorbs the heat and melts, which is why the battery knife can cut it so easily. And if you replace the dry battery with a larger storage battery, the effect becomes even more dramatic. In the footage, the worker clamps both ends of a spring with pliers, and places the pliers onto the battery's two terminals. You can see the spring instantly glowing red. Then with one pull of the pliers, the spring turns into a straight thick wire in seconds. Interestingly, using this same effect, you can even hand make a soldering iron using a pencil and a battery. First prepare a pencil, then shave it open, exposing the graphite inside. Then take two wires, strip the insulation from one end, and wrap them around the pencil core and a metal blade respectively. The other ends of the two wires become positive and negative terminals, and are connected to the battery. At this point the pencil is transformed into an electric soldering tool. Touch it to the blade and it can melt points one by one. It can even weld two blades together very solidly. The reason this phenomenon occurs is that the main component of pencil lead is graphite, which conducts electricity well. When the graphite core and blade touch, a temporary short circuit forms. Due to the heating effect of electric current, the pencil core generates heat. Natural graphite has a melting point as high as 3,600 degrees Celsius, so at that moment the pencil core acts like a soldering iron, transferring heat to the metal blade, causing it to weld together.